Sometimes I've had students ask me what exactly is momentum, and I give them the definition. Well, momentum is mass times velocity, or the product of mass and velocity. But they sometimes don't get that. In fact, many students don't get that. So I then try to explain it to them in a way that they may understand. And I say at that point, well, it's almost like stored force. That if something's got lots of momentum, it has the ability to impart a force on something. Now, you can't use what I've just said as a way of defining momentum in an exam, but it does help understand what's going on. And today we're just going to drill down a bit more in what we mean by momentum and force. So force is actually the rate of change of momentum. That is a way of defining force. You could say it's the rate of change of momentum, and that would be force equals the final momentum, I mean, the momentum that something had at the end, take away the momentum it had at something at the beginning, divided by time taken. Just a little bit of clarification here. When you see the word rate of on the top, force equals rate of, that means time. You divide it by time, and you can see quite clearly there, time taken. The units here are, force has got units of newtons, time has got the units of seconds, and just off the page, momentum's got the units of kilograms meters per second, kgm/s. There we go. Again, an easy way of really trying to explain this idea of having like stored force, the ability to create a force. Let's imagine that we have a car of mass 1,000 kilograms with a velocity of 30 meters per second. And imagine we need to stop it in 6 seconds. We're going to need quite a force to stop it in 6 seconds. And the way we can work it out using the equation, force is final momentum, take away the starting momentum, divided by time taken. The final momentum is basically mass times velocity. The mass is 1,000 kilograms, but the final velocity is 0 because it's not moving. So 1,000 times 0 is going to be 0. The starting momentum was 1,000 kilograms times the 30 meters per second it had at the beginning. So 1,000 times 30 is 30,000. And the time taken is 6 seconds, which you see underneath there. And now if you notice it says 0, take away 30,000. Divided by 6 gives you minus 5,000 newtons. So that's the size of the force needed to stop that car. The minus actually refers to the fact that you are pushing in the opposite direction to which the car is moving. Now, if we treat the same car, but this time stop it in 0.2 seconds, so let's imagine we're stopping it against another car or a wall, it has an accident. So 0.2 seconds is a very, very sharp stop. What force do you need for that? Well, again, you stick the values in there. 1,000 times 0, which is the initial momentum, 1,000 kilograms times 0 meters per second. Take away, 1,000 times 0 is the final momentum. Take away the initial momentum, which is 1,000 times 30, which is 1,000 kilograms times 30 meters per second. But this time the time is 0.2 seconds. And that has an amazing effect on the whole calculation, because this time it turns out in order to stop the car in 0.2 seconds, you need a force of 150,000 newtons. That's to stop the car. Now, if you're traveling at that speed as well, that force of 150,000 newtons, a big section of that is going to be passed over to you. You're going to have a massive force, and of course, it leads to huge injuries. So how do we prevent injuries in cars? Well, car designers will always try to make sure that whenever you have an accident, that less forces are created. And so the way you have less forces is by actually increasing the time of the collision. So if you make time as big as possible, you end up with a smaller force. The other thing to realise is that in a collision, each vehicle, if two cars are colliding, each vehicle will exert equal and opposite forces on each other. And also know that in a collision that momentum is always conserved. Okay, so when we're designing cars, what we'll try to do is we'll try to increase the time of the collision, and by doing so you reduce the force. Okay, so what we do is put airbags. So rather than hitting like a solid wheel or a solid dashboard, which will stop you instantly, the airbag slows you down gradually. It makes T bigger. Seatbelts do the same thing. They seem very, very firm, but they actually stretch in an accident. Again, they slow you down gradually rather than suddenly. Child seats, here's a good tip. By law, you actually have to have any baby seat facing the opposite direction to the parents. And the main reason for this, to be honest, is that if there is an accident, the whole child sort of falls back into the seat, and the time of the collision is spread over a longer time and makes the forces a lot less. At the same time, it serves the benefit of actually you being able to keep an eye on your child. Be aware that you must make sure that the airbag in the passenger seat is disabled, because if that airbag goes off with the child seat there, it can be catastrophic for the child and could actually kill them. So that's not part of the GCSE, but just a live tip. And it's also legally, you must make sure that's the case as well. Also, what cars will do is they'll deliberately have sections of the car that are designed to give way, and thereby increasing the time over which you stop. So, as you know, we said earlier that cars have got kinetic energy, and that kinetic energy has to go somewhere. Now, if the car stopped suddenly and stayed in one neat package, then that energy would be going on you. The energy would be used to deform you. So the kinetic energy is absorbed in these things here called crumple zones, and so energy used to deform the metal. At the same time, it increases the time over which the collision takes place. Instead of taking place in 0.2 seconds, it might take place over 1 second, and so therefore you'll end up with less force being exerted on the car and on the passengers. So there we go. That's how momentum becomes a force. It's basically you change the momentum over a period of time, and that'll give you some idea as to how big the force is. It's well worth practicing. These tend to be the hardest, amongst the hardest questions on the paper.